tree. So let's take a quick look at how you figure that out. Okay, so you have your, ignore most of this figure except for what I tell you about. So here we have species A, B, C, and D. We have their DNA sequence listed to the right of each individual species. And then phylogenetic analysis was done, and this tree over here was the result. A sister to B, C sister to D. But we don't know. We know we have one final tree. This is the tree that the model returned. Were there other, how well supported is this tree? Okay, how much of the data support that A is sister to B rather than an alternative topology? Well, okay, let's say C sister to D rather than an alternative where D diverges, then C diverges, right? So they're not sister here, but they're in descending order here. Okay, so how you get that is you take your sequence alignment here and you make a new sequence alignment by sampling with replacement. So you pull out one column from this alignment. We'll say we're going to pull out this first column with the A's, and we're making a new alignment. And this alignment has A for the first column. Okay, so pull that out. Then we go back in and we pull out the next column, and that column might be, let's see, this one here, U, C, C. Okay, and so now essentially what I'm building up is this sample here where it has, you see this first column of A, all A's, and then this column of U, C, C. Of course, you don't actually take those out of your pool, so the next sample that you draw, you're going to sample this column again, and so you'll see in the alignment you have U, C, C, and then you keep sampling, right? You keep pulling out a random column and attaching it to your alignment until you reach the same number of columns that you had in your original data set. Average gene size for a mitochondrial gene is, say, about 1,100 base pairs, so you'll have 1,100 columns. When you're done with that, you run this through your phylogenetic analysis again. It produces a tree. In this case, the tree is the same tree as this tree here. And so you would chalk up, right? If you did 100 of these, you would say, okay, this tree finds this relationship, so give this node a 1, and give this node a 1, and give this node a 1. If you look at, and then you do this again, right? So you do this for sample 2, you get your bootstrap tree. It also has A and B sister and C and D sister, so now you come back up here, give this a 2, this a 2, and this a 2. It's found, this relationship is found in 2 of your 100 trees. But now you come down here and you say, oh, A and B, that gets a 1, so that's now 3. But C sister to D doesn't get, is not found in this bootstrap tree, and so it does not get another number. So now we have 3 versus 2, and this node also, this node is, you would get a 1 here because even if you collapse C and D, the relationship where C and D and A and B are all closely related and to each other more than to other species in the alignment in the sample, then you still get this node. It's a little bit complicated there, but you keep going, more bootstrap trees, counting up the number of nodes that are found in each bootstrap tree, and that's what your support value is. So that basically looks at, if you had a random sampling of your data, how well supported would this original tree be? You can use your original tree, or you can show a consensus from all of your bootstrap trees and put the values on there. In this example, it looks the same. It doesn't always look the same. Okay, so now you know how to do a bootstrap analysis. So you get an idea of what those numbers mean. So generally we say that anything over 70 is supported with a bootstrap value of 70 or above. Okay. There is another type of analysis called a Bayesian posterior probability. And that is different than Bootstrap. The resampling is not what is done. We're not going to go into how a Bayesian analysis is done, but I will tell you that the meaning of the numbers is a little different. It is not a number from 0 to 100 like this is, like the Bootstrap is. It is a number from 0 to 1 because it is a probability. Most people will actually show you the Bootstrap or the Bayesian posterior probability as a value 0.99, 0.75, 1.00. These two trees, however, don't do that, and I want to make you aware of how that normally is shown, and that's the way that I show it when I use it. So the Bayesian posterior probability is the probability that that clade is true, conditional on the model you used to create the tree, the priors that you implemented, and the data. And the priors are sort of a part of your model, essentially, and then the data are your sequences. So it's a little easier to understand the probability your clade is true rather than a Bootstrap, which is a little bit nebulous because it's that random sampling of your data. I guess it gives you an idea of, like they say, the amount of error that's in the tree. So it gives you an idea of how much noise there is, or how much disagreement there is in the various sites that you sequenced. Okay, so let's go back to ivory-billed woodpecker. So now you understand that the first two numbers are bootstraps. The first one is out of 100 bootstraps, and the next one is out of 1,000. Of course, it's corrected to be a bootstrap value from 0 to 100, and then your final number, this 100 here, is your posterior probability, and it should say 1.00. Okay, so I already went through and told you that a bootstrap value of 70 or above is considered pretty good. It varies for posterior probabilities, 95, 98. Those are numbers that people say are good for showing strong support. So much higher posterior probability is needed than a bootstrap value. If you want to know exactly why, I'd be happy to talk to you about it later. So I would suggest to you to go back through and take a look, highlight the nodes that are not well supported, right? Have a bootstrap value of less than 70. So here, for instance, is one of those, and also has a bootstrap value or a Bayesian posterior probability of less than 90. Don't worry about the Bayesian values. Focus for now on the bootstrap probabilities, the bootstrap values, and just highlight those for yourself and think about if that node were not true, if you had to collapse that, take away this node, which extends this in a line and this node in a line up to this divergence here, then what would that say about these relationships? And we will spend more time on that in class. Okay, let's see if I have anything else to say to you about this. Take a little bit of time to make sure that you're labeling each of the species in here. I've already told you what the species are. The text will tell you what the species are. Label where the species are from to help you understand this. But this tree, you should have marked up like crazy so that you can really understand it. We will spend a lot of time answering questions about this paper. I think that's about as much background as you need to understand this. I'm not going to go through and tell you where to find answers for your message box, because I think you guys are really quite capable at that. So let's move on to the passenger pigeon paper. This is a paper that is very timely right now, thinking about the extinction, the anniversary of the 100th anniversary of the extinction of the passenger pigeon. I don't have a huge amount to say about it. This is a much simpler paper in that they didn't do any dating of their tree, so they're not trying to tell you when these divergences happened. That does limit the utility of this tree and what they can say about it. And I would say that I disagree with some interpretation that they have. And I'm looking forward to talking with you guys about that. So I do want you to pay attention as you look at this tree. Look for these nodes that are well supported and aren't. Let's see, I'm going to point out right away. Of course, here we've got the passenger pigeon. okay? And then here we have some nodes that are not super well supported. Again, we have maximum likelihood, or we have bootstrap replicates above the line, and then below the line are your Bayesian posterior probabilities. So we're looking for bootstrap values over 70, and I'm just pointing out some that are pretty low and are particularly related to where our passenger pigeon is. So you want to think about, if you had to collapse these nodes, what does that say about the conclusions they're making, in particular with reference to biogeography? I would go through and mark this up. In fact, I did from my copy. Mark this up with what do the dark lines mean, these dark lines here that talk about biogeography, North American species, and lighter colored lines. Point out where the different groups come from, so you can look at the pattern of diversification for this group, which is really, this paper is much more about biogeography than the other one even. Okay, I think that's going to be enough to get you through these. Looking forward to having you guys back in class and spending some more time on phylogenetics. I think you guys did a great job on your quiz, and see you soon. Hope you've had a great break.